So this is a continuation of exercise 236, where they're looking for three things. First, is a lone pair localized or delocalized? Second, what's the hybridization of the atom it's on? And third, what's the geometry of the atom it's on? So we got up to E here in previous videos. So for the first step is to draw in the lone pairs. And none of the carbons in this molecule has a lone pair because none of the carbons has a negative charge. Carbon only has a lone pair when it has a negative charge. And then the nitrogen just needs one lone pair to get a total of 8 electrons around it. Remember, there are 2 electrons in each bond. So the question is this lone pair involved in resonance at all? And it is. That lone pair is allylic. It is allylic because if you go one atom over, you're at an atom in a double bond. And in fact, it's allylic in 2 places. So that is involved in resonance, and the implication of that is that it is delocalized. What resonance does is it takes electrons and it spreads them out over multiple locations. Oops. And so the electrons that are spread out in that way, like the lone pair on that nitrogen, are not on just one location. They're on many of them, so they're delocalized. And so really what that means is they're existing in a p orbital there, py orbital. The pi bonds happen because there are 2 parallel p orbitals on those, and it's because that lone pair fits in another pair another p orbital that's parallel with those that it's able to fly through all of them and get spread out over a larger area. In other words, that's the reason for the resonance, and that's the reason why it's delocalized. Now, in order for that lone pair to exist in a p orbital, the nitrogen can't mix all 3 of its p orbitals with the s orbital. It can only mix 2 of them. It has to keep this p orbital for the lone pair. So that means it's going to mix the s with just 2 p orbitals and be sp2 hybridized. And any atom that is sp2 hybridized has a trigonal planar electron geometry. So the bonds, or the electrons I should say, point into the ends of a triangle, and it's flat. So that's that. And then if you imagine that flat pancake, trigonal planar pancake, the p orbital is going to be going up and down through the pancake. So you'd have like the trigonal planar orbitals that are flat, and then that p orbital would go like through the middle, up and down. Okay, how about this next one, last one for this problem. So first step, let's draw lone pairs in. Each of these oxygens needs 2 lone pairs in order to have a total of 8 around it. And we'll go through these one at a time. These lone pairs on the left are those involved in any resonance patterns. And they are. Those are allylic. If you go one atom over, this atom is in a double bond. So those are allylic. Now what that means is that one of those lone pairs can exist in a p orbital that's parallel with the p orbitals in that pi bond. So in this case, they're the py's. So these are parallel and adjacent, so they form that pi bond. If the lone pair exists in a p orbital that's parallel with those, it'll be able to spill its electron density into them and spread the electrons out. But the atom only has one py orbital, so this other lone pair is not going to be able to do that. If it were, it could be in a px orbital, but in that case, it's not parallel with the p orbitals in the pi bond, and it could be in a pz orbital, but again, not parallel with the p orbitals in the pi bond. So this lone pair on the right that's in the py orbital, that one is delocalized. It's spread out over many locations. But the p orbital on the left, that one is localized. It's stuck in that one location. There's no orbital available that would be parallel to these other 2 orbitals. The one orbital that was parallel, the py orbital, is being taken by the other lone pair. Now I just happened to choose the right lone pair to be the one that the p orbital that would to be the one that would go in the p orbital, but it could be either of them, it doesn't matter. It's just one of them is in the p orbital and delocalized, and the other is not in a p orbital that's parallel, and so it's localized. So let's look at the delocalized. Now, in order for that one lone pair to be delocalized, that oxygen has to have a p orbital on it, so it can't mix one of its p orbitals. It can only mix the other two. So if you mix the s with the other two, you get sp2 hybridization, where you get the sp2 mixed Frankenstein orbitals. And any sp2 hybridized atom is going to have a trigonal planar electron geometry. So the electrons will push each other apart to be flat, to be pointing at the ends of a flat triangle. So if the atom is sp2 hybridized, as we've seen, then it's sp2 hybridized, end of story. And any sp2 hybridized atom will have a trigonal planar electron geometry. Okay, let's erase some of this here so we can be a little clearer. So that's what we've got so far. Okay, and so notice you might be saying, well, wait a second, in the first chapter we learned 2 lone pairs, 2 bonds, that's bent. How are you getting these trigonal planar shapes? And you're getting them because this is only bent if it's sp3 hybridized. The fact that this gets stuck in a p orbital, because that's the most stable place for it to be, it lets it spread its charge out. The fact that that's stuck in a p orbital changes the way that the orbitals push against each other, and so that changes the shape that you get. So, yes, if you have 2 bonds and 2 lone pairs around an atom, it normally will be bent, but if one of the lone pairs can be involved in resonance, then it will shift to a p orbital that will change the way the orbitals push against each other, and so it will change the shape of the molecule. All right, let's think about other lone pairs. How about these lone pairs on this oxygen in the middle? Those lone pairs don't fit any resonance patterns. They aren't allylic. They're on an atom in a double bond. They're not one atom away, and they are not one atom away from a positive charge. There's no positive charge right there. And so those are localized. Now, those lone pairs are not in p orbitals, but the oxygen does need a p orbital because it has a pi bond. Remember, every bond after the first bond is a pi bond, and so that oxygen needs a p orbital on it that could be parallel with a p orbital next to it in order to form the pi bond. So it needs one of its p orbitals to stay the way it is, so it can't mix it. It can only mix the other 2 with the s orbital, so it's sp2 hybridized. And any sp2 hybridized atom has a trigonal planar electron geometry. Notice there's a difference between the electron geometry and the molecular geometry. The molecular geometry is the way that atoms look around a central atom. This is not a central atom, so it doesn't have more than one atom bonded to it, so there's no molecular geometry here. But it does have an electron geometry, and that's the shape that the electrons go in, whether they're lone pairs or bonding region. That's the shape that they go in when they push each other apart. Always, the electron geometry will always be trigonal planar for an sp2 hybridized atom. Okay, last but not least, we've got our good old friends, these lone pairs over here. Now those lone pairs are not in any resonance patterns. They're not allylic, they're not one atom away from a double bond, they're 2 atoms away from a double bond, so they're not allylic, and they're not next to a positive charge. So they are localized. No resonance pattern, that means they're stuck in one location, they're localized. And if it's localized, then that means there's no reason there's no energetic reason either of these lone pairs would prefer to be in a p orbital. So all the three p orbitals mix with the s orbital, you get sp3 hybridization on those. And so, because it's sp3 hybridization, you would get two shapes. If you do the electron geometry, that's where you just look at the electrons all as the same sort of thing. So imagine treating these lone pairs as bonds, 4 bonds, that would be tetrahedral. That's the electron geometry. What we learned in the first chapter was the molecular geometry, the shape that the atoms look like. The shape that the atoms look like, and that shape here with 2 lone pairs and 2 bonds, that would be bent. So I would accept either of those shapes if you listed them. So those are the localizations or delocalizations, the hybridizations, and the geometries for all the lone pairs in those molecules.